Okay, so here are my solutions for the FRQs. They may not be fully correct, but this is a blind look at them. So same formula sheet as usual. Nothing changed. Okay, so number one is, let's see. Okay, so a cart is on a horizontal surface attached to a spring. So there's no gravitational force involved, no outside forces. The other end of the spring is attached to a wall. Cart is initially held at rest. When the cart's released, the system consisting of the cart and spring oscillates. So it's held, has potential energy out at this point right here. Figure 2 shows the kinetic energy of the cart spring system as a function of potential energy. And we can see it goes from 4 joules of potential to 4 joules of kinetic, just back and forth. For A, on the graph of kinetic energy K versus potential energy U, the values are the same. I don't think they're looking for that much here. I would think just conservation of energy. And really the main reason here is that there are no, there's no external work occurring. So there's no gravitational forces affecting, there's no friction force affecting it, anything that would be causing that to go down otherwise. Once we look at the points, that's where you might have to add some more, but I can't imagine they're going to go that far beyond just conservation of energy and saying there's no external work or no work done by external forces might be a better way to say it. I should adjust that. We're going to say it's not okay. So clear that up. Okay. When the cart is at positive L and momentarily at rest, a block is dropped onto the cart. This is actually very similar to number, I think it was the paragraph response 2018. It has a similar feel to that. Block sticks to the cart and cart system continues to oscillate. The frequency before it's dropped is F1, after it's dropped is F2. So, nice thing is they use 3, which means it'll be 4 times the mass. So, our period, so first we need to figure out the period, then we'll solve the frequency. So I know my period equals 2 pi root m over k. And that square root goes the entire way up. So I could say my initial one, we'll say is t1 equals 2 pi root, we'll just say m naught over k. We don't know what k is, but the spring constant will be the same either way. That should not have any bearing. Our second one, so our t2 we'll say is 2 pi root, but now I've got 4 m naught over k, which I could then take out a 4 on the top, make that a 2, so that gives me really a 2 pi root m over k, which actually would then, I could say that t2 equals 2t1. So my period of the second one is double the period of the first, which makes sense because we know heavier masses make things oscillate slower. Our numerical value then, so I know that my frequency is the inverse of my period. So I could then say that if I know t2 over t1 is equal to, let's see, that'd be a 2, then I could extrapolate that my f2 over f1, since they're both inverses, should be equal to 1/2. Basically, the frequency being the 1 over time unit, it's going to make it where it should flip diffraction. We could actually do it more thoroughly going back to our initial equation and setting it up to say that I could also write, if I wanted to, I could say frequency equals 1 over 2 pi root k over m, and solve it this way. We'll get the same result if we do that. We'll factor out the 1 over 2 pi root k over m naught, and we'd have a 1/2 left over on our F2, which means F2 over F1 would be just a half over 1, which would be 1/2. Part C, the dashed line in figure 4 shows the kinetic energy K versus potential energy of U after the block is dropped on the cart. Graph is identical, and explain why the two must be the same. My main focus, I would imagine, here is going to be that our potential of a spring is equal to 1/2 kx squared. It is not dependent on the mass. So adding extra mass at the end of that spring is not going to give it more potential energy. Since energy is still conserved in both cases, we know that the kinetic would be the same. Let's say energy as it oscillates is still conserved. And 2, after the block is dropped onto the cart, consider a system that consists only of the cart and the spring. So let's go back and look at the picture. Okay, so now we're ignoring that 3 m0 weight on top of it is the idea here. On the figure 4, sketch a solid line that shows the kinetic energy of the system that consists of the cart and spring, but not the block after the block is dropped onto the cart. So we know some things are going to be the same. So the big thing is our kinetic energy is 1/2 mv squared. So if we know that it has that proportional to mass, if I've made it where the mass is 4 times bigger on the entire system, including the weight, we were up at this 4. But because I really only have m0 instead of now 4 m0, I'm actually going to have a graph that's going to be more aligned looking like this. And ideally here you use a straight edge, make it a nice straight line. So in that case, it looks like energy is not conserved. It's really still going to be conserved. It's just less apparent because we're not looking at a closed system. This is now an open system, which makes it a little different. Okay, and that's all of question 1. So going back to scoring, we've got a total of 7 points. My guess is this is probably going to be 1 point just for conservation of energy. I should make that an actual number. There we go. Okay. I don't see them giving 2 points for this because there's too many other points to give out here. And I cannot draw a circle today. Let's try this again. For the second part, I would imagine this has got to be at least 2 points just because we've got to first use the equation. So we'll just change this to blue. We'll say, I'm just going to set this on a flat surface. I would guess we'll have probably 1 point. Let's actually get a pen that is a color. For correct periods / equations. 1 point for the ratio. I would imagine it'll be 2 points. So if you had the ratio reversed, but you did the work correctly, you would still get 1 of the 2 points. So up to this point, we have 3 of the 7 points allocated. On this one, briefly explain why 2 graphs must be the same. For sure, that's going to be at least 1 point, obviously. Which is basically saying that it is going to be... I would bet this is actually going to be 2 points. And the reason for this, I think we're going to have 1 point for using our... That's not... It should be a U instead of S. So 1 point for using our potential of energy correctly. And possibly 1 point for conserving still, which gets us to 5 points. The last one, sketch a solid line that shows the kinetic energy of the system. I would bet this is actually going to be 2 points, which sounds like a lot, but we probably have 1 point for the y-intercept and 1 point for a straight line. to indicate it's a linear function. It's not going to be a curve or anything. Even though it says solid line, I would imagine I still want to ensure that you actually drew a line that needs to connect the potential at 4 joules to the kinetic at the left. And again, the reason that potential would be at 4 is because it's still that same 1/2 kx squared displacement. Adding extra mass did not affect our potential at all, but it did affect how much that potential turned into kinetic for the cart itself. The overall system kinetic energy was split between two pieces, but at its max potential, that energy is really stored in the spring at that point versus in the cart or mass. So that gives us our total 7. I could see maybe they might do a second point for number 1, but I just don't see a good way they could actually argue that. And I think the best spot for that extra point would be on the number 2 here. For the second one, the cart going down a ramp. Let's see, they conduct an experiment to determine acceleration A of a cart. My first thought, we might have something going on with an mg sine theta down the ramp. Cart's released from rest at the top, moves down the ramp. X-axis is parallel to the ramp. So that's kind of what I know I've always taught in my classes. We kind of invert the axes. So this is our positive y direction. That would be our normal force as well. Whereas our weight acts kind of at a slight angle to that. The x-axis is defined to be, and the origin is at the top. Students collect the data shown. So they've got the position as it goes down the ramp, and they've got times. Indicate which quantities could be graphed to yield a straight line whose slope could be used to determine acceleration. So if we kind of think back to kinematics formulas, that's what we're going to need. We've got a few options. So we're trying to find the slope to determine the acceleration. So I need something that is going to really include acceleration and includes displacement. I think our best bet here is going to be our x of t equals, I'm hitting the wrong part of the pen. Let's undo that real quick. Equals, we got 1/2 at squared. Our v naught t, it says it started at rest, so we can ignore that. And our initial displacement is 0, so we can ignore that as well. So really, this is what our formula comes down to. Just x of t is 1/2 at squared. And once we see this, we could then graph x of t versus t squared, because that means our slope should be equal to a over 2. If any of you have used the Logger Pro, the picket fence lab, this would be the exact same thing. We could look at when you do the calculations, you get the slope is 4.9, and that is why it's the same way. In this case, it's not going to be 4.9 because it's a ramp, but that'll be for a later part. So I might do is out here, I'm going to label I'm going to call this t squared. And we'll put our t squared values in here. So let's get our calculator. Keep pressing that button that I don't need to press. Okay, let's see if we can get that away. We got 1521. Our next one was at 0.59 squared, which is 0.34 each one. I've got 0.77 squared, which is 0.5929. And these, I would definitely carry all the decimals just to be safe. I know they allow you to do rounding within reason, but it's going to be helpful on the graph to have a more precise value. 9216. And 1.2 squared is 1.44. That actually I did not need a calculator for, because that's just 12. So we only really need to do x and t squared. We have that left column. We should not need to fill that in. You could do something to adjust the over 2 part, but I would not worry about that quite as much. But for my vertical and horizontal, my vertical I'm going to make be my, most likely that will be our output. We'll say that's our position. So because I want to make it where it's my rise over run is my slope. So let's see. Yeah, so I want to make my output is my vertical. That's going to be my x of t. My horizontal axis is my t squared. And again, I know the slope is actually going to be half of the acceleration, so we'll have to adjust for that as well. But that should be in a later step. And yeah, in part 3 right here is where we can find our a from that. So we've got, let's see, what was my biggest t squared value was 1.44. Usually I want us to fill at least half the graph. So I got 1, 2, 3, 4, 5, 6, 7, 8. If I did on 0.2 intervals, that gives me 1.6, which gives me a nice full graph. We'll do 1.4, 1.2, 1. This would be 0.8, 0.6, 0.4, 0.2, and 0. On our y-axis, that'll be our position. We go up to 0.55. I've got 1, 2, 3, 4, 5, 6, so we'll just do that 0.1s. Historically, scoring guides have always said these graphs need to fill at least half of the graph, so I'm trying to make it as close as I can to the full part. It also will help the readers to make sure they can see everything. Okay, so let's make sure we've got everything. We plot the quantities. We'll do that in a second. Clearly scale and label all the axes, including units. So this will be our t squared, and we'll just say it's second squared. And this is our x of t, which is in meters. So I've got my scaling done. I've got my labeling done, just to make sure that that is all covered. And it says to draw a straight line. Since it was asking to do something that yields a straight line, we should be able to get a straight line here. So I've got, first one is 0.15 and 0.06. So that's going to be right there. Our second point was 0.35 and 0.6. We know it's 0.35 and 0.14. My third point was 0.59 and 0.24. So we see right on 0.6, and we're going to be right about there. This is also a good way to make sure what you're doing is correct. If you don't get a line, we know we messed something up. I've got 0.92 and 0.37. So we're going to be just a hair over here and about right there. And then I've got 1.44 and 0.55. 1.44 is out here. 0.55 is right in the middle. Looking at that, I think I've got a pretty good line going. I will have to go ahead and see if I can get a line tool. So we're going to go ahead down here. Let's go find a, how can I do my line? Shapes. And we don't necessarily have to start at the origin. I don't think it's gonna hurt if we do. If I draw that line, you can see we're gonna get a nice line going through there. We'll put it about right there. And I wonder if I can make that smaller. It's not gonna let me. Okay. Let's go ahead and actually try to change that line real quick, make it a little thinner. We'll do a red one just to make it different. They don't care about color, but it should help this to be a little easier. I'll make our line. There we go. For their lines of best fit, they just want to see it reasonably close. Typically, you should have it where about the kind of points are evenly spread on top and bottom, so about right there maybe will be good. We're not going crazy precise, but where it is clearly a straight line. In theory, should go through the origin. I don't know they're going to be picky on that, but it wouldn't hurt to have it there. Just because we know that if there was at 0 time squared, there should be 0 displacement. So that wouldn't be a bad spot to start. I'm just having a hard time getting this to work exactly on the computer. With your ruler, it should be pretty easy. Our last part is using the line you drew, calculate an experimental value for acceleration. Here, I would just use slope formula. We know our last point is probably going to be the easiest one to approximate with. So I might say that was 0.55, I think? Yep, 0.55 and 1.44. So my slope was, let's see if we can make this larger again. Go ahead and actually resize this window. Because I went up 0.55 over 1.44. And that equals my slope. But remember, that was equal to 1/2 a. So if I want to get my actual a, I would need to double that, which would give me a equals 1, let's say 1.1 over 1.44. And then we can reduce that down. We should also be fine to leave it like that. And our unit would be meters per second squared. We know it should be less than 9.8. That's kind of our starting point. It's a pretty shallow ramp, which makes sense if it takes 1.2 seconds to travel a half meter. We know if we drop something in free fall, it'll go 4.9 meters in a second. So it's going pretty slow. So I feel pretty good with that. B, they're asked to determine an experimental value for acceleration due to gravity g. We already talked earlier that my expectation is to set mg sine theta as a force down the ramp. So really our acceleration, we could say, should equal g sine theta. Since if it's in free fall, sine of 90 is 1, which means acceleration is just g. This goes back to any ramp section you probably have done with the trig breakdown. So we should definitely, we need to know theta, or theta is a big one. And then my expression, I already did that. I could say that my experimental g would be, I'll say g equals, what is it, a over sine theta. The idea is if we know acceleration and we are given the angle theta, we can solve backwards and get g. Just to be safe, we might say exp, just to clarify that's our variable. Next, C, the student calculate the value to be significantly lower than the accepted value of 9.8. What's a physical reason other than friction or air resistance that could lead to a significant difference? Let's go back and look at the lab. So we're saying no friction, no air resistance. Those are my first two go-tos, and with that out of the picture, it makes it a bit trickier. So this one is actually, I think, the hardest part of this question so far because I'm not 100% sure what they want. Because it could have, so it could be, I mean, the common errors I could think of just based on the variables we have is going to be, was the timing correct? The distance measurements, I would think that'd be easier, and ideally, if I was making this experiment, I would probably use video analysis or Logger Pro or some sort. Other factors we'd have, so they took out friction and air resistance. I'm not really sure what they're looking for in this because I can really not think of too many other good physical reasons here. Let's put a question mark here because that is a kind of a weirdly worded question. I'm just not sure what they're looking for. I mean, you could argue where you're at on Earth, but I think it's only like 9.78 on top of Mount Everest. That's not going to affect anything. Let's see if there's anything else in the lab design that would indicate it. They have the cartridge release from rest at the top, moves down the ramp. It's parallel to the ramp. Origin is at the top. They got position, they got time. Yeah, I'm really not sure on C1. Then C2 is kind of the same thing because I just don't know what they're looking for there. So that one I'm going to put a question mark. I don't know the answer to that, so we may modify that later. Students want to confirm that the acceleration is the same whether the cart rolls up or down the ramp. Start the cart at the bottom and give it a push so it rolls up the ramp and momentarily comes to rest. X-axis is still defined to be parallel. They want us to sketch the position and the velocity. So our position now, initially, it should have been a downward parabola, kind of starting here, falling. It would have started at actually 0 and curved upward because down the ramp was positive. So now what's going to happen is, remember, initially it would have started here, been like basically an x squared style graph like this. As the time increases, that position is going to increase faster. Now we're starting actually with some displacement. So we might start like here. It doesn't say how high it goes up. Momentarily comes to rest. I can imagine we definitely don't want it going through the x-axis, because if it goes through the x-axis, that implies that it flew off the top of the ramp. So I might start it here, kind of draw my little parabola. Have it go like this, and it's going to curve back up. And on our velocity graph, it's going, remember, to the right was our positive, so that's the big thing we have to watch for here. So we're actually starting it with a negative push, and it's actually going to have an increasing slope, just like this. So it's kind of weird because typically our velocity is the other direction, but because downhill is labeled as positive, it's actually going to end up starting with a negative velocity that's going against the positive direction from up here. And then as it goes back down the ramp, it's going back to positive. Other things we could label is we could say this is like, that's our, we'll say T1, and we'll say this is T1. They're not going to care about this, but it would never hurt to include that just to specify that when it hits that horizontal tangent, we also see it's going to have 0 velocity. Okay, that's it for that question. That was a 12-pointer, I believe. Yep. So let's go look at scoring possibilities. So the first one, we've got our, let's see, indicate which quantities can be yielded. And it says you may use the remaining columns to record quantities. You don't have to. So I would bet we're going to have at least 1 point. Let's make that a little thicker. For graphing x of t versus t squared. There could be a second point for not having any extraneous ones. I don't know they're going to. And just to be safe here, let's include this as a second squared. Let's see, using columns. And let's say, actually we'll say 1 point for the values. And maybe a point for the units. I think getting 3 on this would be kind of generous, but I bet it's for sure at least 2, maybe a third point. This one, we've got 1 point for we'll say reasonably sized graph. We'll probably see a point for a correct plot. We'll see at least 1 point for a line that's reasonable. And again, I would try to make sure that line does connect to the origin just to be on the safe side. Because they might specify they want to see it go through the origin. I don't know they're going to because there were no data points there, but it might help. So we're already at 6 points now if that was the way it's broken down. And we'll say reasonable and straight. This one also may be earned if the actually, I don't think they're going to. They could try to offer some points where if you had the incorrect graph or incorrect data above and you still plot it correctly, you might get the first 2 points, but you would not be eligible for the third unless you actually make a line, is my guess. For this, the experimental value for acceleration, I'd probably say 1 point for just solving for slope, and 1 point for acceleration as 2 times the slope. So that gets us to 8 points. So we've only got 4 points left, so I think we're going to have to go back and modify this. They will need theta. That's going to be 1 point for theta. And this will probably only really be 1 point. I just don't think they have enough points left. And really, that equation is pretty straightforward. I don't think they're going to go that crazy on it. They're not going to have like 2 or 3 points for setting it up because that's a very common equation we've seen. So that puts us at 10. These, I just don't know how they're going to do this. I would bet they're 1 point each. I just don't know what they're going to ask there. Because that already put us at 12. And this will probably end up being probably 2 points, which gets us 14. So we're actually going to go back and modify and get rid of this one. I don't think that's going to apply. So we got x of t and t squared. And actually, I don't even know if they're going to include this. The key word here is you may use it. So the idea there is, hey, this is free space you can scribble on to get ready for the plot on the second part. They're not going to grade your answers here unless you show up on the graph, I believe. So I think that's just 1 point for saying, did you correctly plot x of t against t squared? You might earn something if it's inverted, but I would imagine they have to be in the right order. Because that gives us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is our 12. In this, I think we're going to have 1 point for an upward parabola For our displacement, we'll probably also have 1 point for a linear velocity with a negative y-intercept. And they might even say on upper parabola that starts down. I think they are going to be picky on that because with that initial push, we need to show that as we go through here, it gets pushed, it goes down, comes back up. And then on the velocity, it goes up, comes back down. Velocity, it's going to go up the ramp, stop, come back down. I think they will be very picky on not just the general shape, but actually where the location is. There was one in 2021 that they were picky in that same way of it was, I think, a motorcycle jumping over some buses or something. But that gets us 12 points there. That one, I just think part C is going to be a very low scoring part of it. I don't see many people getting that right. But the graph one shouldn't be bad. The plotting one should be pretty straightforward if you have done linearization. If not, that'll be a big differentiator. And then these equations should be pretty common for most people. Part 3, block of mass M is on the end of a spring of spring constant K naught attached to a rod. So the rod can rotate at various speeds. So we've basically got some angular stuff going on here. When the rod's not rotating, it's at rest. Its unstretched length is L, so there's no potential at that point. All friction forces are negligible. Okay, let's see what's going to go on. So at time t is t1, it's spinning, so it goes in a circular path with constant tangential speed. Its stretch distance d. This is basically your tetherball type question. But instead of your tension pulling in, now it's a spring force pulling in to make you go in a circle. Time is t is t2. It's going a similar way, but now it's a larger distance. It does not specify the speed. I bet they're going to ask about the speed. So on the following dots, it's at that point on the far left. They want us to draw the forces exerted. We know it's a centripetal force. A centripetal force is going to be center seeking, so we should have an arrow on T1. It's going to point towards the center, just like this. Because it's on the left, it's going to be pulling to the right to pull back to the center. On T2, it's going to also start at the center, but now it's going to be pulling more. So all we need to do is make sure the arrow is bigger. It does say relative lengths to make sure you indicate that. So let's see if we want to add anything else to that. That should be all we really need. It's only the force exerted on the block by the spring. So we don't need to worry about the normal force or gravitational force opposing on the table. All they want is the force on the spring, or force by the spring. So referencing D1 and D2, we could say that, let's see, at D1, it is closer. So the spring has less stretch. Meaning less force. We can include that the force of the spring equals, we can say negative kx or absolute value of kx. It's not really going to make a difference here. The big thing is that magnitude is going to be larger, which means the arrow is bigger. Let's see if there's anything else I want to add. Yeah, I think that's probably sufficient. And by saying it's closer, we could say it's closer than D2, and that would kind of give us our full points there. So at D2, further, therefore, we'll say f of S2 is greater than f of S1. And just to be specific, we'll make these magnitudes. Reason we're mentioning that is that spring forces are technically negative forces. If we don't do that, they could argue that it's the wrong direction. Is the tangential speed of the block at time t is t1 greater than, less than or equal to speed v2 of the block at time t equals t2? So coming back to here, if it's got that bigger radius, then we know that we have to justify without using equations. So I like to use equations to kind of process through it. I know that my tangential speed is going to be, let's see, let's start with my centripetal force equals mv squared over r. which means I could then say RFC over M equals V squared, which means that when I've got the bigger radius, it makes a bigger velocity. I've got more spring force, which makes a bigger velocity. I've got the same mass, which has no effect. So I know that my velocity in the second one for sure is going to be bigger. So it should be this guy. And I would just say, we can say the bigger radius. I don't know if they mentioned the speed of rotation. Actually, the second one has to be spinning faster to make that same spring extend. So we'll say the bigger radius should lead to greater velocity for sure. But we want to justify without equations, so we can't use our equations on this. What I almost might do here is say, if we said, let's say, I could even say if my D1 approaches 0 and we'll say D2 approaches infinity, then that would mean our V2 has to be bigger than V1 because V2 is not equal to 0 and V1 is approximately equal to 0. We could go something along that route. There's a couple ways they're going to look for here. The big thing is what are they going to look for on the scoring? I think they're going to be looking for, is that proportion set up correctly where you could say that the change in radius or the change in force will make that velocity larger. That's my best guess, at least. Oh, and then on here, here's where I actually get the equations. Consider a scenario where the block travels on a circular path with a spring is stretched to distance d from its unstretched length L. Want to know the net force exerted. And we can again ignore our normal forces and our weight because they are acting equal and opposite. They would not affect the net force. So my force is going to be, let's see. I know I've got, it's really just equal to my centripetal force, which is my mv squared over r. But we have to figure out what's contributing to that, which is really our kx, our spring force. So now let's see if we can, what do I want to do with this? Okay, so it's try a circular path with spring distance d. And our x here is actually a d, so I could really say I don't really know how much extra we're going to need on this. Because if I know the spring constant, my k, and I know my distance, that's really all I need to find the net force because everything else is kind of integrated inside that. I don't think that's going to have a major shift. This part we will use in the next piece, I believe, but we don't need it here because that is just kind of what that force makes. It's not really the actual part of the net force exerted on it. And really those are values we can't calculate quite as easily, whereas this we can. So I think this honestly might be sufficient. One thing they always love to do is they throw extra variables you can use, you don't necessarily need them. If you look at the other ones, unstretched length L, I don't see a reason we need that because our spring force is based on how far it's displaced from rest, not the overall length of the spring. Our mass, I don't think we're going to need because the spring force shouldn't really get affected that much by it in this case. Yeah, I don't see a reason the mass would have any major effect here. It will affect the centripetal, although actually I think it's going to cancel out, so it won't really even matter there either. Okay, equation for the tangential speed of the block. So now we're going to use that second part. So I could say m naught, we'll say v squared over r. And my r here is going to be, this is actually the radius of both the L plus D. The reason is that's the actual radius of rotation. That's the size of circle it makes. easy way to think about that is if that spring was 100 feet versus 1 feet long, that 100-foot spring is going to have a lot bigger radius, which means that it's going to have a much bigger circle it's mapping. It'll have a much larger tangential. So L plus D, and that equals my K naught D. Again, we don't need any like G or anything here because it's all horizontal. It's not going to come into play. Next, I need to solve for V, so that gives me K naught D L plus D over M naught. And that's going to be a square root equals V. And that should be sufficient. C, does your equation agree with your reasoning? So, easiest way to look at this is we reasoned that in the other part, our V2 is bigger because the radius is bigger. If we look at this on the top, I have the distance here. I got the distance, and it's actually a squared quantity, so it'll actually get factored out if we wanted to. Or no, it can't factor out because of the plus. But the big idea is that the spring constant is the same. The mass is the same. The length is the same, but that D is bigger. So because that distance is larger, we can say yes, as we'll say as D increases, V increases. We don't need to even specify that it increases linearly or quadratically or at a square root rate because all they're asking for is, does it agree with our reasoning? We said here that V2 is bigger than V1. Down here we can say that when that distance gets bigger, our velocity gets bigger as well. That agrees. That's all we have to say. Okay, going back to points. Now this should be a 12-pointer for the qualitative. Yep, let's go change to blue. Okay, so A is just instructions. So here we should have, I think it's going to be 2 points. I'm going to say 1 for pointed right. We got 1 point for clearly larger at T2. They could add a third point about only having no unnecessary vectors. But I think in that first one, they'll probably say 1 vector pointed right. So that would kind of cover all those pieces at once. Each one should only have 1 vector, and the right one should have a larger vector than the left one. Your reasoning for drawing the arrows lengths you did. So we said that, let's see, we're going to probably have, I'm going to say we have 1 point for different displacements. Probably 1 point for spring force. And maybe 1 point for showing let's say FS2 is bigger than FS1. And again, I don't think they would pick you on the absolute values or magnitudes, but it's worth including. So we're up to 5 points out of 12. Is it greater than, less, or equal? So we got probably 1.4 correct. And then this is kind of in line with, it was the 2018 FRQ about the block falling on it. They usually have 1 point just for did you pick the right choice. And then we need a justification, which I would say is the radius increase leads to velocity increase. So going back to check our point totals now, we're up to 7 out of 12. So I got 5 for this page, which might be too many, but we'll see. This one was just the F net, so it's really just spring force is all we're looking at in the proper terms. So making sure you don't just say F equals KX, that's going to be a very common response. It says to express it in these terms. If you don't do that, you probably will lose points. And then this one, I'm guessing we're going to say 1.4 F spring equals FC. 1.4 the derivation of V. And then this last one probably have 1.4 agreement. And this, I would imagine, can be earned with a no if your equation doesn't. Actually, this one's probably going to be, you have to get, it's probably an all or nothing question now that I'm thinking about it. Because I've seen these historically where it'll be, you cannot earn points, they both have to be correct to earn a point. So I'd imagine it's going to be 1 for the agreement correctly. We'll say correctly. And probably 1 point for the explanation. And we'll say with D and V. The reason you have to specify those is looking back at this equation, K naught is constant, M naught is constant, L is constant. The only thing changing is D. So we have to make sure we say that when D increases, V increases, and that agrees with our reasoning. If you said D increases and V increases and that does not match your reasoning from earlier, or that makes your earlier one wrong, they might give a point, but I would not bank on that. But that should give us our total 12 points. Question 4, we've got a block on a string wrapped around a pulley. It's going to be unwinding. I know we actually did one of these in our classes where it was the with the vernier multi spoked pulley. Block of an mass attached to a long lightweight string. Specifying this just to show that as it's falling, it's not changing the inertia on the pulley. Wrap several turns around it, mounted on a horizontal axis to its center, so there's no weird parallel axis theorem or anything kind of wonky. Pulley is a uniform solid disk of mass m and radius r. They give you the inertia, which they always will for these. It can rotate about centered negligible friction, so there's no external torques acting on it, which makes it a bit easier. Does not slip, so you don't have to worry about anything kind of funky from that. When it's released from rest and as it travels to the ground, the magnitude of tension is Ft. This is actually not too dissimilar in a sense from the toilet paper freefall lab, because you've got, as it's falling, it's unwinding. It's just that it's kind of in reverse. So let's see what equations we could use. It says to use M, R, F, T, and physical constants. So, okay, so it's I think it's pulling out about the outside of it, right? Yeah. So first I'm trying to think, okay, they gave me inertia. I've got MR, my tension force. So let's just think about what we have. We'd say, just kind of thinking equations, and we'll just kind of reason through it. I got T equals I alpha. We'll start with that. Think, could that give us anything? So I'm just kind of jotting down some equations that might be useful. My other torque is RF. And it's really RF perpendicular. It's pulling perpendicular to the pulley, so we're good to go on that anyways. So if I try to use this, I think this is our best starting point because our torque is fully provided by the hanging mass. I think we can agree on that. And since the pulley is not moving, we don't have to worry about anything really weird going on there. So my radius is R. So I could say R, and then my force, does it say what the mass is? Unknown mass. I'm going to say unknown equals I, which is my mr squared. We'll just fill that in really quick. Or it's 1/2 mr squared alpha. So we still don't know our mass, but I think we can actually work that out in a second. I have an idea for that. Because it gives us that tension exerted on the block by the string. So if we think about that block, I've got a block hanging down. It's got a tension force F of T, which tells me that really that's equal to my, we'll say M unknown times G. I don't care about necessarily what the unknown mass is because it says I can use f of t. So remember, this is our RF sine theta, and this will really be R m unknown g. But we're going to replace that and just say it's going to be R f t equals 1/2 m r squared alpha. And now we can solve out for alpha. Again, making sure we keep our letters just to be consistent. This is actually alpha d, just to be specific. So as I work that across, I can cancel out one of the squares. I can cancel out the radius here. Gives me a 2ft, moving the 1/2 across, over my mass of the pulley times the radius of the pulley, equals my alpha d. Checking back, I use m, r, ft. I didn't need any physical constants. It's solving for alpha d, so we should be good to go. They did not specify which direction is positive, so I don't think you need to necessarily flip signs or anything. Scenario 1 and 2 show different pulleys. Same solid disk reference, has a hoop that's same mass, same radius. Big thing here is that weight is more distributed towards the edge. So this is I'm just going to note this is a larger inertia. Our full equation would be the 1/2 m r2 squared minus r1 squared, I think. We don't need to use that here. We just know that if that weight is further to the side, it's going to make the inertia larger. It's free to rotate about its center with negligible friction. All that's the same. They're both pulled with the same constant force. If it's the same constant force, that's like a hanging block. 2 is going to go slower for that same time interval. After that interval, the change in angular momentum of the disk is equal to the change in angular of the hoop. But the change in rotational kinetic for the disk is greater than that of the hoop. Okay. So let's think about these. So angular momentum is L equals, it's similar to mv, so it's going to be, this is our I omega. This is also where you should probably use your formula sheet to be safe. And our rotational kinetic energy is equal to, it's like 1/2 mv squared. Our mass is replaced with inertia. Our v is replaced with omega. And we'll just write it this way. We could also write it as omega being v over r if we wanted to. Yeah, because so if v equals r omega, I could say v over r is omega, which could be useful here. I don't know that we need to, but it could be helpful. So just kind of going back to the question here. So same constant force for the same time interval. We know the disk is going, or the hoop is going slower than the disk. Just kind of think about how we're going to reason through this. After that, the change in angular momentum of the disk is equal to the change in angular momentum of the hoop, which makes sense because if it, let's see. Yeah, okay. So what's going to happen is if the hoop has a larger inertia, has the same change in momentum, it has to have a lower change in angular velocity, which means that since the angular velocity is squared, that'll have a larger impact than the increase in inertia. Then we're going to try breaking this down just to see. If I have 1/2, actually no, because they don't give you the equation for that, we're not going to worry about that. So we'll start our response. So at the end of the time interval delta t, so you could say at the end of interval let's see how I want to say this. And both of them having, I want to check our formula sheet just to make sure I'm not forgetting an equation. Let's go see. Okay. Oh yeah, I was figuring we might have an equation. We're going to actually use this guy as well. Delta L equals torque delta T. That's going to be super handy here. Let's come back down. So we've got delta L equals torque delta T. So we could say that both have the same change in angular momentum because the same, we'll say T equals f of a times my radius was r applied over the same delta t. Therefore, delta L equals torque delta T implies same delta L for both. But we could then say, since the hoop mass is, we'll say it's pushed to the edge, we could again argue with the 1/2 mr2 squared minus r1 squared, but you're not expected to know that formula. I don't think it'll be required. Just saying the mass is more pushed to the edge. We know that the inertia of the hoop is greater than the inertia of the disk. Even with the same mass. And then we could say, since L equals I omega, the disk will have less omega, less angular velocity. And unfortunately, my pen is huge. But as we keep going on, we could say then that since we'll say rotational K E equals 1/2 I omega squared, we'll say if I is 2 times larger for hoop, omega is 2 times smaller. Therefore, that gives me my omega squared is 4 times smaller. Therefore, the rotational kinetic energy is 2 times smaller. So we already did that hoop was smaller than the disk. That's logically the same as saying that the disk is larger than the hoop. So that should be sufficient. Looking at scoring on this one, typically the paragraph is at least 5 points. I think that trend is going to uphold here. So first, determine an expression. I would bet this would probably be 2 points. We'll have probably 1 point for I would bet using the torque equations, or using some expression that handles torque. 1 point for saying for the correct derivation for alpha d. This may be kind of funky scoring one. I think very few will get both points. This is going to be all or nothing for part A. For part B, we're going to need, let's see, 1 point for, it's going to be the same change in angular. We're going to see 1 point for, or actually, we're going to see 1 point for same T, or same torque, and same delta T. 1 point for the same angular, 1 point for, I'm going to say, I and omega relationship. So as I gets larger, omega gets smaller, and so forth. Actually, in that case, we can't really fit that one in. We'll see why in a second. 1 point for different inertias. 1 point for the different omega implies different rotational KE. And 1 point is always for a coherent response. So even if you made a mistake somewhere, as long as your reasoning made sense at some level, then you'll get a point for that. And that's historically how they've always done it. So this one, it's always hard to guess exactly how it's going to be, but it's kind of thinking, okay, sentence by sentence, we need to ensure that they have the same change in angular momentum. We know that because it was the same time interval and the same torque. We know that the angular momentum, if they had the same change in angular and they both started at 0 because they were at rest, that means that they're going to end up having the same actual angular momentum at the end because they started with nothing, both ended with the same thing. When the inertia is bigger, angular velocity is smaller, and vice versa. Since the hoop has a different inertia, they did not specify it had different inertia, but that is expected that you can derive that from the image. Then that means that it'll have more inertia, means less angular momentum or angular velocity. Less angular velocity then means it's going to have less rotational kinetic energy. Last one, Rob, the sphere is on a horizontal mounted axle, carefully balanced so it rests in a position vertically upward from the axle. Let's see. Okay, the axle is horizontally mounted. So this is almost like your vertical circle tension question, except for you don't have a rope, so it can actually almost come to rest at the top. Sphere is lightly tapped. Rod sphere system rotates clockwise about the axle. Does not say it rotates at a consistent rate because it will not because of gravity. It says no, they are not equally spaced apart. That is true. In which frame is the angular acceleration the greatest? Angular acceleration is alpha. And this is going to be where it's going to have the greatest change in that, which should be where we have the largest force applied. If we think about what forces are applied, the main force in the angular sense should be when it's horizontal, which I would think is going to be right here. Just because at the top there's very little acceleration. At B, it's gaining speed. C, it's gaining the most speed. D, it's going to start actually slowing down, which is still an acceleration, but it's not accelerating as fast. At E, there is no acceleration because there is no net force acting on it at that point. So I would say C, and we can really say because torque equals RF perpendicular, and our F perpendicular is greatest at C because our force due to gravity and the radius are perpendicular. You could also say RF sine theta and say that it's an angle of 90 degrees and theta is maximized, or sine is maximized at 90 degrees. In which frame is the kinetic energy the greatest? Our rotational kinetic is 1/2 I omega squared. In this case, the I is not going to matter, inertia is not changing, but we know that the omega is our angular velocity. That should be maximized at the bottom because up until that point it is gaining speed. So the axis is the axle is a big hub piece, should be E. And I would actually use just energy conservation here. We could say it's E because all potential in system has been converted. I don't think we need to go anything beyond that. I think that should be sufficient. You could argue it's accelerating up to that point. It's kind of slowing down once it passes, but if you just say the energy is converted fully at that point, that should be plenty as well. B, the rod sphere system has a mass m and length L. I want to see how many. Okay, cool. Mass m and length L. Center of the mass is located at distance 3/4 L from the axle. Derive an expression for the change in kinetic energy of the rod sphere Earth system from the moment shown in frame A to the moment shown in frame E. So I could say delta KE is really equal to my change in potential, right? Because it started with a bunch of potential and no kinetic. It is lightly tapped. That implication is it's basically enough to dislodge it, but it's not enough to give it any measurable amount of kinetic energy. So we got 3/4 L. So my change in potential energy is mg delta y. Reason we're saying delta y is because we have a change in height. It started 3/4 L above. It finished 3/4 L below. So I actually get a 6/4 L is my delta y. I got my g. I've got my m, which is a mass, which is right here. So I should get my change in kinetic energy equals, I'm going to do a little bit of simplifying. It gives me, I got my m, g as my physical constant. I'll actually put a 3/2 in front just to move it out. 3/2 mgl. And then explain why the rod and sphere gain kinetic even if Earth is not included in the system. So the reason I'm specifying that if the Earth's not included, that means that there's actually no potential. Because potential is derived from the gravitational force. If the Earth's not in the system, then the Earth doesn't technically have a potential energy. I don't know. We need to go too far on this. If it's supposed to be we could say if it's not a closed system, it gains energy from, I'm going to put that in quotes, an external force. That one's kind of a weird worded question. I'm not a huge fan of that. But basically what's going to happen is as it falls, if you just ignore the Earth is there, it's not going to mean the thing's not going to fall. It's still going to gain energy from an external force because it gains velocity. I'm guessing that's what they're shooting for, is there's some velocity change, because I don't know how else they're going to argue that, really. Okay, so coming back scoring, we've got 7 points. We've got, what, A1, A2. Okay, so we've got 4 total parts. So this will probably be 2 points. I think it's going to be 1 for C and 1 for using torque in your explanation. I don't think you have to go crazy on that. Again, they're going to look for, that's where it's perpendicular, that angle is 90 degrees between the radius and the force exerted. Any of those should be sufficient. Where is the rotational energy of the rod sphere system the greatest? This was, I forgot to label that. That should be, it's frame E. So I think it's also going to be 2 points. I have 1 for frame E. I think we're going to have 1 for, I'm going to say just conservation of energy. Because they're looking for, in this one there may be some other options. You could argue that after that point it starts to have acceleration going the opposite direction of the velocity. Conservation of energy is by far the easiest way to explain it and the most surefire way to get points. So we're 4 out of 7 points so far. On this, we've got our derivation. I would assume this is going to be 2 more points. 1 point is going to be, again, conservation. And probably 1 point is going to, and that would be, and I would bet 1 point is derivation. I don't know how they're going to break up that exactly. They might include the, because you just say change in kinetic equals change in potential, and then I think the second part is actually solving that change in potential out. Because all we did from here to here is I just simplified a fraction. It's a pretty quick derivation. And then our last one that leaves only 1 point left, which is going to be something about, I would say, your change in velocity. Because the velocity is changing, we know that there has to be a gain in kinetic energy. You could say delta V, you could use change in omega. You could say there's acceleration. There's a couple different ways to say that. But that should cover all those questions. Again, this one back here, I'm actually going to pause and see if I can find someone else's argumentation because I just didn't like, which one was it? This one. So we'll come back and resume here in just a second. Okay, so coming back to that one that we didn't like. So it was saying that we cannot use friction or air resistance. So I think timing would be an option. The other one I actually debated earlier, but I didn't really like, is we could say our theta measurement. So if we think about how those would impact it, if the timing, really the timing and the displacement shouldn't be that hard to measure because you're just measuring it on a ruler. I think this is our bigger one. A common one I've actually seen in our labs is, say you have your track like this. Your height is really a change from here to here, right? So it's actually the same as this change here. And this is our, we'll say it's our x. And then we'd have to use trig to find our angle theta here. To make it a significant difference, we'd have to figure out how that would affect it. If our G experimental was smaller, let's see. That would need to be that sine theta. So as the bottom, it gets larger. Actually, let's see. If the bottom gets larger, the whole fraction gets smaller. So if we overestimated the angle, let's say overestimate theta leads to smaller G experimental. And the basic reason that would be true is if you think about a ramp on the Earth versus the Moon, for example, to make the same acceleration, that ramp on the Moon has to be way steeper. So that's the only way I can really think of it, because everything else, it said no friction, no air resistance. Mass has zero effect on it, so that's not going to come into play. There's really nothing else we could point to unless you said your timing was off or your distance was off. And you could hint at those. It's just kind of preference at that point, just saying what could you find as a source of error. It's weird because typically these experimental questions, they want you to actually build the experiment. They really didn't ask us to do this. So they might be just saying, okay, is there any sort of, basically say, okay, can you think of what source of error there could be in a lab like this? And that's my best guess. But that should be it. So hopefully this is helpful.